here are some rules. The second rule. So you notice the first rule is the one I just mentioned. And then the next one says if you have a constant function, then its derivative is 0. Does that make sense to you? Why?
Because if it's like a constant, it's just a horizontal line.
Okay.
And if you take the derivative of that, it still is not existent.
Right. So understanding, here's an example, right? Y equals 4. If y equals 4, then the graph, well, 1, 2, 3, 4, looks like this. Maybe I'll make each line 2. It's a horizontal line. And so now, the slope of the tangent line, well, if it's horizontal, and you say, what would a tangent line look like? I don't care where you draw your tangent line, it's also going to be horizontal, right? So what's the slope of that tangent line? 0, because the slope of the line itself is 0. That's fine. So that's a geometric way of understanding this rule. But you wonder, is there another way of understanding it? Well, remember, we can always go back to the definition, right? If I say f of x now is 4, and I go ahead and I try and compute f prime of x using the definition, limit as h goes to 0 of, well, f of x plus h minus f of x over h. Now when I go to fill in the items, my denominator is h, my numerator, I'm going to be subtracting 4 because that's what we said the function was. Right? But what is f of x plus h? Well, that means anywhere there used to be an x, you put an x plus h, but there are no x's, right? So what does f of x plus h also equal? 4. I don't care what you put in as the input, the output is always 4. That's what we mean by a constant function. You guys with me? So look what the fraction becomes. 4 minus 4 over h. What's that equal? There's a proof that the derivative is 0. Any constant function. It doesn't have to be 4, it could be 14, it could be anything, right? So there we have a basic rule. And this is the idea, is can we create lots of shortcuts? I'd like to be able to find the derivative of all kinds of things. I mentioned this one already. The derivative of the sine is cosine. That was on your worksheet. Okay. It turns out, wouldn't it be great if the derivative of cosine was sine? It's not. It almost is. What's the derivative of the cosine function? Negative sine. So close. So close to being beautiful. But again, these things, I'm kind of pushing ahead here. This is really after exam 1. I'm not going to make you responsible for the trig functions yet on exam 1. But I will tell you that if you wanted to prove the last one, you'd do it exactly like we were doing in the group work and that page that I referred you to. We'll probably do that for a homework problem at some point. Okay, moving on. This is an important one. By the way, any time in this class that you see me use the letters U or V, I'm usually talking about functions of x, like f of x or g of x. This is u of x and v of x. And really, I guess this is two rules in one. You could put a plus sign between functions, or you could put a minus sign between functions. And the point is that to find the derivative, well, okay, so let me help you with this one. Again, what's the rule? The rule is, let's do plus. The derivative of u of x plus v of x is equal to, and by the way, has the book used this symbol for derivative yet? d dx? Yeah? And has the book used this symbol? Well, yes, we've all used the prime, right? So these are remnants of the creators of calculus, all right? This is Newton notation. Newton used prime. And this is the notation that Leibniz used. He used what are called differentials, that little dx in the bottom of a fraction. All this means is take the derivative. Well, it does mean something slightly more. It means with respect to x. In other words, I'm telling you that x is the input of the function, which is obvious because I wrote it out. But remember, in the formula I had on my slide, I just wrote u and v. But I'm telling you here, oh, the input of these functions is x. Does that make sense to people? Okay. And both notations are used all over the place nowadays, and so you really need to learn both. Okay. So what does this say? If I have a sum of two functions, you can find their derivatives separately. And that's very easy to verify using our definition also. The fractions could come apart, basically. But now, that means, well, I can find the derivative of lots of other things now. So I could find, for example, the derivative of x cubed minus x squared plus x minus 4. Let's see if you could find the derivative of that polynomial. Oops. So I'm hoping you're getting the right answer. In the front here, I do bing, bing, 3x squared. Then I'm going to write the minus sign down. Minus what? 2x. Plus, this may be tricky to some of you. What's the derivative of x?
1.
Y. Why is it 1? Well, because automatically, what's the exponent that's up there? A 1. So bing, you bring it down. And then bing, you get x to the 0 power. But what's anything to the 0 power? So that works. That's nice. And then we already learned that the derivative of a constant is 0. So this would be the derivative. 3x squared minus 2x plus 1. You guys follow? Moving on. Oh yeah, that's good stuff. I want to skip that for now and go to your book. Let's do that. So, we covered the constant and power rules. This is one that I haven't done with you yet. If you have a function and it's multiplied by some constant out front, the question is, what's the derivative of that? C times f of x. And you notice the answer is c times f prime of x. It's almost like you can ignore the constant if it's in front of a function. And they show you why, because you could just factor it out front of the fraction and bring it past the limit. Because there's no h. When you have a constant, there's no h anywhere, so you could just bring it right past. And so that's their rule, this theorem 3.4. This is really a proof of the rule. Okay? And so, you know, if we go back to the work we were just doing on the paper, right? Think about the function we just found the derivative of, right? We had, let me call it f of x. F of x was x cubed minus x squared plus x, and then I had minus 4, right? So now I can say the derivative f prime of x is 3x squared minus 2x plus 1. That's what you guys just computed. What if I said I want the derivative of the derivative? And by the way, this is something we'll do quite a bit. We'll want to take multiple derivatives in calculus. Because when you do the derivative, you just get a brand new function. So how do you do it? Well, first of all, notation-wise, With Newton, it's pretty easy notation. You call it f double prime of x. Okay? So that means the derivative of the derivative. And what that rule tells me about the constant multiple is that, you see this 3? I can just ignore it. I'll just bring it down. And I'll just find the derivative of x squared. So what is the derivative of x squared? 2x, right? Same thing with this piece here. I will write down minus 2, and I'll just find the derivative of x. And what's the derivative of x? 1. We did that. And then, of course, the derivative of 1 is 0, because any constant, when you take the derivative, you get 0. And so I guess the second derivative would be given by 6x minus 2. We okay with that? So next it's I can find these derivatives, and the question is, well, what can I use them for? So example 4, here's my function, right? This 2x cubed minus 15x squared plus 24x. But it's funny because, you know, they write that down, and then they find the derivative, but I may not be that quick yet. So I say, hey, when you're reading this, read it with a pencil in your hand, you know? Let's write down example 4. And so here it is. And now I need to take the derivative. So f prime of x equals, well, bring down the 2. The derivative of x cubed is 3x squared. Bing, bing. Minus 15. The derivative of x squared is 2x plus 24 times 1. There we go. And so this derivative is equal to 6x squared minus 30x plus 24. Right? And so part B says, where does f of x have, this was part A here, find the derivative. Where does f of x have a horizontal tangent line? That's the question. So I can take 6x squared minus 30x plus 24. That'll give me the slope of any tangent line. And what I do is I set it equal to 0, because I want the tangent line slope to be horizontal. Does that make sense? Now you're just solving an algebra equation, right? This is exactly what my algebra class is doing this week on their test. They have to solve these. So you want to look for the greatest common factor to make it easier for yourself. So we'll take out a 6. Minus 5x plus 4. Oh, okay. X minus 4 times x minus 1 equals 0, right? So it looks like there's 2 places that this function will have a horizontal tangent line. It'll have it at x equals 4. It'll also have it at x equals 1. And did they draw me a graph? I guess not. Oh, yeah, they did. Figure 3.21. There's a picture. Let's find it. Where'd she go? There it is, right? So where are the horizontal tangent lines? Here's one of them, x equals 1. Here's another one, x equals 4. What do you notice about the horizontal tangent lines and their relationship to the function. Max and mins, right? This horizontal tangent line happens to be at a place where there's a minimum value. It's the smallest thing around. And that's very characteristic, and that's actually one of the reasons that derivatives are so important. We always want to do things like maximize or minimize a function. We're trying to optimize. And so this can help you do that. Go ahead, Nugget.
This is the sum, right?
This is, say it again.
The sum of
Well, there's actually several rules going on at once, okay? And they all have different names. Yes, it's the sum rule because when I did the derivative, think about how we did it. We found the derivative of 2x cubed, 15x, negative 15x squared, and 24x separately. That's the sum rule. It's also the constant multiple rule because I brought the 2 down. But in terms of which rule is which, for these rules, I almost don't care what they're called. I just want to make sure you know how to do it.
I was just wondering if those created sometimes in the notes.
Yeah.
I kind of say it's got the constant power rules. That's why they're written that
Oh, yeah, from the book.
down. Yeah.
Let me see that. So this one, oops. This example is example 4 from talking about, slopes of tangent lines. Okay? But we did use the sum rule also. Sure. We did constant and power rules too. Okay? So let's see. Calculating derivatives. For the following functions, find f prime using the definition, then determine an equation of the line tangent to the graph of f at a, f of a, for the given value of a. You know, maybe I should start talking test right now. This is a fair test question. It's from section 1 of chapter 3. And a couple things to say about it. They give me a function. F of x is 2 over 3x plus 1. And they give me a value of a. And so I guess one question is you know, at this point, I don't think there's an easy way to find this derivative, okay? Not without getting a few more rules. So I understand part A is to compute f prime of x using the definition. If they say using the definition, at that point, you want to pull out that limit, okay? That's what they want you to do. And then when they go to part B, part B says, what do I have to do? I need to determine an equation of a line tangent to the graph of f at a, f of a. Okay? So again, find an equation of the tangent line at the point a, f of a. Of course, for me, a, f of a, well, I guess I know what a is, right? So a is the point, or is the value -1. What I'd really like here is f of -1. Okay? And I'll give you a hint of what we're going to do for that. But when we get there, you're going to use what's called point slope form. That's probably the easiest way to do it. And so that would be y minus y1 is equal to m times x minus x1. I think that's probably the easiest way to do this problem. Okay? But I can't do anything if I don't have the derivative. I need that in order to find the slope. So let's do part A. I mean, they gave me these problems in this order for a reason. Okay, so I'm going to use the definition. So I told you guys, hey, when you are doing these problems, let's write down the definition and then we'll begin to learn it. Okay? F of x plus h minus f of x all over h. And I'm going to take the limit as h approaches 0. Okay? And so now we need to try and fill in what this is. Okay, so I tell people, hey, first thing I'm going to do is put the h in the denominator. That's easy. And then the next thing I'm going to do is I'd like to fill in this minus f of x, because that's also easy. It's minus 2 over 3x plus 1. Right? Now what people sometimes have trouble with is this, f of x plus h. That just means everywhere it used to say x, you're going to write what? X plus h. And when you put it in, leave the parentheses around it, because that's the number that is getting multiplied by 3, for instance. And so this first fraction is 2 over 3 times x plus h plus 1. Does that make sense, Jocelyn? Okay? You guys with me? And now it's a matter of, can we simplify this big mess? Now, advice. Here's the next thing I recommend. Write down limit as h goes to 0. And one thing that makes this problem really challenging, all the fractions involved. But instead of writing fraction minus fraction divided by h, there's another way to handle divided by h. Instead of dividing by h, I can multiply by 1 over h, right? Dividing by h is the same as multiplying by the reciprocal. And so what I'm going to do is I'm going to write these things down again. So this first fraction, I guess, is, well, 2 over 3x plus 3h plus 1. And the second fraction is 2 over 3x plus 1. Notice I have those in a big parentheses, and I have then all that gets multiplied by 1 over h, and then I have the limit as h approaches 0. You guys with me? At this point, the only challenge is the algebra. It's not really the calculus. We filled things in. And so now you just have to know your rules about fractions. So can I subtract these fractions? I can't unless I'm able to get a what? You need a common denominator, right? And sometimes I kind of panic. I'm like, well, how do I get a common denominator for that situation? And so I go over on the side over here, and I remember when I used to do 2/3 minus 4/5. What's the common denominator? Well, how'd you get it, though? You multiplied them together, right? That'll always give you a common denominator. Even if it's not the least common denominator, it'll give you something. So you guys know how to do this one? Then you know how to do that one. Get the common denominator. You know, when I do this problem, I teach my students, this guy gets multiplied by 5 over 5. This guy gets multiplied by 3 over 3, and then it works. You get 10/15 minus 12/15. You guys with me? Same thing here. This one, what would I want to multiply top and bottom by in order to have a common denominator? That 3x plus 1 over 3x plus 1. And I would want them in parentheses. And then my common denominator is going to be 3x plus 1 times, well, whatever 3x plus 3h plus 1 is. So I'll need to multiply this one by 3x plus 3h plus 1. That makes sense, doesn't it? And so now we just have to work it out. Maybe I'll pause and let you guys try and crank that out, and we'll see where that goes. Anyways, let me finish this up so you guys have this example worked out completely. So let's see. This is the limit as h approaches 0 of 1 over h times, all right, what does this mess become? Let's see. Let's leave the denominator as, well, 3x plus 1 times 3x plus 3h plus 1. And the numerator up here, I guess I'm going to get 6x plus 2 on that side, right? And for the other piece of this, do you guys see that I'm distributing negative 2? Right? So it's minus 6x. Make sure you wrote minus 6h and minus 2. If you didn't write those, then you missed the negative. So let's see what we get. Well, we get the limit as h approaches 0 of 1 over h times what? I think the only thing left in the numerator is negative 6h, right? Yes or no? Okay. So then in the denominator I have 3x plus 1 times 3x plus 3h plus 1. And see, if you were to plug in 0 now for h, you'd still get 0 over 0, telling you that maybe there's something you can do. And the something I can do is I can cancel these h's, right? Because those are two fractions that are being multiplied. And so I'm going to get, let's see, the limit as h approaches 0 of negative 6 divided by 3x plus 1 times 3x plus 3h plus 1. And so the derivative of this function, f of x, that I started with, ends up being negative 6 over 3x plus 1 quantity squared. There's the answer to part A. Good? And so let me write it up here. Part A, the answer is f prime of x is negative 6 over 3x plus 1 quantity squared. It's a lot of work, but I got it. So now part B. Find an equation of the tangent line. All right. So I said we're going to use point-slope form. Let me try to do that. Oh, we have a problem already. It says I'm supposed to do y minus y1. So I write down y minus, now where it says y1, I want to put this, but I don't have that yet. Derek, you have a question?
Yeah.
They tell me what goes here is f of a. So I better go up to the very beginning, take the function, and compute f of negative 1, because that's what a is, right? Let's compute that. We get 2 over, isn't it negative 3 plus 1? So that's 2 over negative 2. So I'm getting that the other coordinate of the point is negative 1. Evidently, this curve goes through negative 1, negative 1. You guys with me? Okay. I also claim we're going to need to use the derivative we found. Why? What's that going to help me find? That's for the slope, right? So the slope that we want is going to be f prime of negative 1. So let's work out what that is. negative 6 over negative 3 plus 1 squared. So that's negative 6 over negative 2 squared. That's negative 6/4. And so I'm getting that the slope we want is negative 3/2. So I'm going to use that too. I'm going to use this here, f of a, and the slope is going to be negative 3/2. So now I think I'm ready to write down the answer. An equation of the tangent line is given by this. Y minus, oh, wait a minute. What should I write? Yeah, so you could either write y minus negative 1, or you could write y plus 1 equals, and then my slope we said is negative 3/2. And then in parentheses, I'm going to write x, what? Minus, well, there's negative 1 again, right? So let me write plus 1. And there is an equation of the tangent line. I guess the last thing I'd like to do is just pull out a calculator and kind of check that this all seems to work. Okay? So, here's my calculator. Let me turn it on and go to the y equals screen. And so, let me type in the original function. 2 divided by, open parentheses, 3x plus 1. Let's see what that looks like. Okay. It's a rational function. I should have known it's going to have an asymptote at negative 1/3. Let me zoom in. I'll be able to see things a little bit better. Okay? So there's that. And now I guess I'd like to draw, I'd also like to graph the tangent line that I came up with. So you can do that if you look at this line. Remember that to put it in the calculator, you need to write y equals. So let's see if this makes sense to you guys. Minus 1 to the other side. That red equation is one I can write, for example, in y2. You guys see what I did? I took my equation I just found, but I just subtracted 1 from both sides, and I can put it in my calculator. So let's see, negative 3/2, and then times, open parentheses, x plus 1, close parentheses, and then minus 1. Enter. Wow. There it is. Does that graph hit at the right place? Well, I can find out. And here's one nice way. You know, you could hit trace and you could start tracing the curve. But if you hit second trace, that's the calculate menu. And you can compute different values, but you can also find where curves intersect. That's kind of a nice feature. First curve, y equals 2 over 3x plus 1. Enter. Second curve, the line. Enter. Do I have a guess? Ooh, this is where I better try again. There's a problem because of the way it's trying to find the point of intersection. Let's do that again. Choice 5. First curve, 2 over 3x plus 1. Second curve, the line. Do I have a guess? What you need to do is you need to make your x value close to what the intersection is. Looks like it's around negative 1.1. Oh, wow. Not finding it. I'm surprised. That's interesting to me. I mean, the intersection is at negative 1,1. We worked it out. But it's fooling the calculator, and Unfortunately, I can't really say why until we get to, well, chapter 4. So let's do it one other way, maybe. We'll try to second calculate a value when x is negative 1. What's the y value? Negative 1. And that's true whether you, no matter which curve you use, the curve or the line. They both go through negative 1, negative 1. So 71, they say verify that f of x equals x to the 1/3 has a vertical tangent line at x equals 0. Verify that it has a vertical tangent line at x equals 0. Now, unfortunately, for you guys to calculate the derivative, I don't know how they wanted you to do that. Because how many of you tried using the long definition like we did at this last problem? And I don't know that you can get it. You know, you could try something like multiplying by the conjugate. I've done this. But I'm not sure it goes anywhere. But now with our shortcut, what can we do? What's the derivative going to be? Bing. Bing. We really haven't proven that that's the derivative. We've done it for integers and we did it for the square root. It turns out it is the answer to the derivative. Okay? So now, do we believe that that has a vertical tangent line at x equals 0, and why does it? Well, let's think a little bit about this curve. The cube root of x is what that really is, right? Let me again use the calculator and sketch a graph. So I'm going to keep my windows the same as they are, and I'm just going to type in, well, x caret 1/3 power. That's the cube root of x, and I'll graph it. So you can see, you know, as you're looking at this picture, this function, I would say, is always increasing. If I'm driving a car from left to right, I'm always going uphill. But as I get closer to 0, do you see how it's getting steeper and steeper? Or as I move away from 0 on the positive side, it gets less and less steep. And the claim of the problem is that right here, at 0, if you were to draw a tangent line, the tangent is vertical. That's the claim. Actually, that's very interesting because it might make you wonder, what does this really mean, tangent line? Again, the claim is that f of x looks like this. This is, again, f of x equals x cubed, x to the 1/3. And the claim is that at 0, the tangent lines grow so much that it has a vertical tangent line. But see, you might not have ever thought about a tangent line going through the curve. But if you drew a vertical line here, wouldn't it have to go through the curve? Yeah. A tangent line is a line that hits the curve in how many points? 1 instead of 2. A line that hits the curve in 2 points is called a secant line, right? So it is possible for a tangent line to go right through the curve. Now to see that, I guess what we need to do is think a little bit more about this. This gives me the slope of the tangent lines, right? Let's write that out using the other notation without exponents. We have 1/3. And then the fact that this is a negative exponent means I can write it as 1 over x to the 2/3 power. Right? Or another way to write this is that the derivative is given by 1 over 3 times the cube root of x squared. That's the derivative. Okay? Now, I guess I would say the following. Note, this is 71. Notice f prime of 0 is undefined. That's clear. But what can we say about the limit as x approaches 0 of 1 over 3? How do I want to do this? I guess I'll write cube root of x squared. That's really what you want to think about. F prime of 0 is undefined, but maybe we can take the limit as x approaches 0 of the derivative. Well, okay. I'm going to take a very small number close to 0 and put it in for x, right? Can I please have a very small number? 0.0001, also known as 1/10,000. Also known as 10 to the negative 4. Okay, 10 to the negative 4. When I square 10 to the negative 4, I wrote it that, I said it that way because that makes it easy to compute. What do you get when you square 10 to the negative 4? 10 to the negative 8, right? Because you're taking a power of a power. The point is, it's even smaller, right? And I'll take the cube root of that, and then I'll multiply it by 3. I'll have 1 over an extremely small number. Well, when you take 1 and divide by something extremely small, the answer is extremely large, right? And so is that enough of a proof for you? I mean, if I want an actual proof for every epsilon greater than 0, right? Or actually, since we're doing an infinite, we're trying to show that this is infinite. For every number n, there exists a delta. But again, that's kind of beyond what I want to do here. Okay? I'm going to leave it like this and just say that's enough. Part of the reason. So what we're doing here, it says use this identity. Hey, that's the one from our song, right? And the fact that the limit of the sine of x is 0 to prove that the limit as x approaches a of sine of x is sine of a. All right, so there's a couple of facts here that they're mentioning, and if this were a test question, I would consider this a stretch question, for sure. They gave me an identity. That's one I really hope you guys know. Okay, at least by the time we're done with this course, you're going to need that. And it says this: the limit as x approaches 0 of the sine of x equals 0. Well, how do we know that?
That just follows as a fact.
Yeah, how do we know that fact? Well, I'll tell you a couple things. It's done in the book. So I might go back and look at that before we leave today, so we understand it. By the way, do you guys know what the sine of 0 is? What's the sine of 0? We want these to be automatic. What's the cosine of 0? Sine of 0?
0.
Okay, so the sine of 0 is 0. So actually, once I prove that that is true, what does that imply? What does that imply? Look, guys, we have the limit as x approaches 0 of the sine of x is 0. Again, that's done in the book. But we also know that the sine of 0 is equal to 0, right? So if the limit as x approaches a of sine of x is the same as the sine of a, what does that prove? Continuity. Sine of x is continuous at x equals what? A, which is 0, right? So that's the first thing done, is if you have those two facts, then we know that sine of x is continuous at x equals 0. Now the point of problem 95 is to say the following. To say that, in fact, sine of x is continuous at any value of x, or every value, right? That's what we're trying to prove here. And so they give me a hint, and so maybe I should go back to the hint. Let's see. They say, well, they say use that identity, right? And then they give me the hint. All right. Let h equal x minus a. I'm going to want that. And then you can get x. All right, so here we go. So let's write down my identity that I'm going to use. Sine of x plus h equals sine of x cosine of h plus cosine of x sine of h. Right? And now, let's see. We know that they say let h equal x minus a. So if I do that, let h equal x minus a, so that x is equal to a plus h. That's what they said, right? Now, what does that do for me? Well, I guess a little bit. And it says, then you want to write the following. You want to note that h goes to 0 as x approaches a. Okay, so I guess what I'm going to do here is I'm going to compute the limit as x approaches a of the sine of x. I'm going to hold the screen down here. We want to show that sine of x is continuous at any value of x. So, like x equals a. A is going to be some random value. I want to show it's continuous. So what I'm trying to show is that the limit as x approaches a of the sine of x is equal to what? Sine of a. This is what I want to come up with. All right. So now the point is, I'm going to take this black and try and make it equal the sine of A. And from their hint, x is equal to A plus h. So we're going to plug that in here. This equals the limit of the sine of A plus h. Not x anymore, but A plus h when I do this. And the point is, if x is getting close to A, this is getting close to A minus A. And A minus A is what? 0. So h is getting close to 0. So you need the fact that this is equal to that. Actually, that's kind of like what we did in the derivative. First time we did derivative, we did this. F of x minus f of a over x minus a, limit as x approaches a. That was our first idea about slope of tangent lines. Do slope, and then take the limit as x approaches a. But eventually, what do we start putting in the denominator? H. So as x is approaching a, that's like h approaching 0. Done. Out of time. So finish this later. I'm not holding you after.